In the last video, we talked about what a differential equation is and how it's useful and why you would want to learn it. But in this video, we'll be talking about the different classifications of a differential equation. Now, there are 4 different classifications. We have the type, we have the order, we have the linearity, and we have the homogeneity. The type refers to whether the differential equation is ordinary or partial. Now, if we have an ordinary differential equation, wrong color. If we have an ordinary differential equation, you'll typically see the notation of dy over dx, have y prime, where we could have the first derivative of y. These are all different ways of expressing a first derivative with respect to x. Now, these are ordinary differential equations. This is the ordinary notation, but then we also have partial differential equations. Now, partial differential equations are typically written with this little hook symbol right here, so we could have the partial of x with respect to with respect to z, or we could have x sub z. And this is a different way of expressing a partial differential equation. Now, we'll go over in later videos what that actually means and how they're different from an ordinary differential equations. But for now, this is a good way of understanding what type of differential equation we have. From there, we go over the order. So you could have a differential equation, let's say dy dx. You could have dy dx, and this would be considered a first order differential equation. This would be considered a first order. Now, why is this a first order? Well, this is a first order because we've only taken the derivative of y with respect to x once. But what we could do instead is we could take the second derivative of y with respect to x. Now, this means we have taken the derivative of y with respect to x twice. So this would be considered a second order differential equation. Another in different notations, we could have y triple prime. This would refer to the third order of a differential equation. So this would be third order. And as you go up in order, and let's say you have, for some reason, you encounter a eighth order differential equation, traditionally the notation will be written like this, or it will be written like the second order, but instead with an 8. So this would be the eighth derivative of y with respect to x. So this would be an eighth order differential equation. Now, when we talk about linearity, I've thought about the best way of describing this, and I came across this definition, which I think best sums up linearity. Now, linearity is described as a differential equation, I'll abbreviate DE for short, is linear in y if we can write it in the form, this will be our form right here, in the form a sub n of x the nth derivative of y, the nth derivative of y, the nth derivative of y with respect to x. And then after this, you would have n minus 1, and so on and so forth. But then we'll skip all the way over to a sub 1 of x times the derivative of y with respect to x plus a sub 0 of x times y. Now notice what's happened here is that the 0th derivative of y with respect to x is actually just y itself. You know, we haven't taken the derivative of it all, so it would just be our y function right here is equal to g of x. Now what does this mean, right? So let's go over what we have here. So you'll notice that we have a sub n of x. This just means that the a sub n, the nth term of a, is made up of only x terms. That's what this x means right here. It's only made up of x terms. There are no z terms, there are no y terms. It's made up of exclusively of the term x. Now, if we go all the way down here, you'll notice that we have a sub 1 of x, a sub 0 of x. These are all only made up of the term x. And then they are attached to their respective derivative depending on what term it is. And then we have other than the derivatives, right? These are pretty self-explanatory. They're just the nth order derivative, and they go down and down and down until we go to the last order derivative, the 0th derivative, which would just be y. It would just be our original y term. And then we have g of x. Now g of x, you'll notice, isn't attached to any derivatives and is exclusively just g of x, right? It's only made up of x terms. There are no y's, there are no z's. It's just g of x. Now, this is the proper form of a linear differential equation. But other things to notice that aren't explicitly said but are shown is that y and its derivatives are all of the first power. Now you'll notice here that we don't have y squared, y to the 15th. We don't have dy over dx to the 3rd power. We don't have the nth derivative of y to the 8th power. These are all to the 1st power. Now that's very important when it comes to linearity, and probably one of the most important parts is that our derivatives and y are all to the 1st power. And we went over this, but it's important to know that the x right here, the function a of x, is exclusively made up of only x, and it isn't made up of any other terms, especially not made up of the main term y. Right? And so this so we have two classifications, and they are either linear or non-linear. Last, we go over homogeneity, and I seem to have taken up more space than I would have liked with my linearity, but that's okay. That's okay, because we have an eraser. These are great. I use them quite often. I make a lot of mistakes, so I find myself constantly using it. We're going to go over homogeneity. So this refers to whether or not a differential equation is either homogeneous, and based off of our previous examples, I bet you can guess the other classification, non-homogeneous. They really went all out here with the naming of these different classifications. Now, homogeneity, the definition that I'd come across for best describing homogeneity is actually quite complicated, but once you start to do a few examples, you'll notice that it's actually quite simple. So the definition is a differential equation. I should have abbreviated that. I'm quite slow at writing. A differential equation. I went ahead and I skipped ahead because I've noticed that I'm quite a slow writer. So I went ahead and wrote this out. Plus my cat came in and stepped all over my keyboard, but that's okay. So we have a differential equation is non-homogeneous if there are any terms separated by a plus, minus, or equals which do not include the dependent variable. Hey, hi, Jay from the future here. I noticed while I was editing this and rewatching the video that I just made, I realized that I have the explanation skills of a malnourished salamander. So I'm gonna go ahead and say this out in a more coherent term. So if you'll notice that in our first example, we have xy prime plus 2y is equal to sine of x. We do have indeed an additive term. We have an additive term right here in our sine of x. It doesn't include any dependent variables, our dependent variable being y. Since it does not include any dependent variables, we can go ahead and classify this as a non-homogeneous differential equation. In our next one, we have the same first left-hand side of our equation, xy prime plus 2y, but you'll notice that we got rid of our sine of x term. Since this was our additive term, I went ahead and I removed it, and since we removed it, now this is equal to 0, this is considered a homogeneous differential equation. Our third example here, we have x squared times y triple prime plus e to the x plus 6 over x times y is equal to 0. You'll notice that we have another additive term here, this term right here, and it doesn't include any dependent variables of y or its derivatives. So since we have it and it's additive and it's separated by a plus or minus or an equal, in this case we're separated by a plus, we can indeed conclude that this is a non-homogeneous differential equation. Now, these are our different classifications. So we have, just to reiterate, the type, the order, the linearity, and the homogeneity. Now, even if these haven't quite made sense to you yet, or if they're not clicking, or you're saying to yourself, Jay, what are you teaching me? This is a little bit too much. It's okay. I also included some examples I wanted to go over just to make it a little bit easier. So we'll go through a couple of examples, and maybe after these examples, you'll get the hang of it a bit more. So what we're going to go ahead and do is we're going to go ahead and classify all these different examples that I have pre-made. Again, I wrote them out already because quite the slow writer, and I'd hate to put you guys through watching me write all these out. So the first one we have is cosine of x, y prime plus sine of x, y is equal to 2 cosine to the third power of x times sine of x minus 1. Now, first we're going to go over the type. Now, you'll notice that we don't have any partials here, so this must be, and we only include ordinary differentials. So this is an ordinary differential equation. We have an ordinary differential equation. So let's go ahead and check our order. Our order is going to be our highest differential or partial. So our highest differential here is going to be the first order right here. It's going to be the first derivative. We only have first derivative y. I don't see any second derivatives or third or fourths. So we must have a first order differential equation. Now let's check if this is linear or non-linear. Remember, if we go back to our definition real quick, like let's just hover over a differential equation in y, if we can write it in the form of a sub n of x. So we have, remember, attached to every one of our derivatives, we have a function of only x, of only x, of only x. So let's go ahead and check that. So in this first one, we have a y prime here. Notice that this function is of only x. I don't see any other terms here. I don't see a y term here. I don't see a z. I don't see any dependent variables included in this term right here. So then we have sine of x right here. This is of only x again. Y is equal to 2 cosine to the third of x, sine of x minus 1. So we notice that this is our g of x term here that I referred to. So this is our g of x right here. And this is our 0 of x. And this is our a sub 1 of x. And you notice that they're only made up of the term x. And then we have our derivatives right here. So I guess based off of our definition, this indeed would be a linear differential equation. Now, if we take a look to whether this is homogeneous or non-homogeneous, remember, if we have any additive terms that do not include the dependent variable, then this is a non-homogeneous. And we do indeed, we have an additive term right here. This whole term right here that's separated out doesn't include the dependent variable y. So this would be a non-homogeneous equation. Let's go over the second one. So in the second one, you'll notice that we have the third derivative of y with respect to x plus y squared times the second derivative of y with respect to x is equal to 14e to the x squared. Now this looks very messy, but if we go through it step by step, we'll be able to figure this out in no time. So we have the type, right? If we look at the type, we have only ordinary differentials here. We don't have any partial differentials here. So go ahead and classify this as an ordinary differential equation. Our order here, so what's our highest order? This would be the highest derivative. Highest derivative in this case, we have a third derivative right here. So let's go ahead and call this a third order differential equation. Now, is this linear or non-linear? If we look at it, we go back to our definition just one more time. We have to have a sub n of x in front of every one of our derivatives. They have to be of only the term x. And then at the end, we have a g of x, which does not include a dependent variable. So if we look at this and we notice that right here we have of the terms only x. So this would be our a sub 3 of x. This would be it right here, but there's nothing here. So, we don't have to worry about it. This right here, though, is our a sub 2 of x. And we'll notice that this isn't of x, this is of y. We have a y term here. We have a pesky y term there. And since we have a y term there attached to our dependent variable y, then that means that this is indeed a non-linear differential equation. Non-linear, because we have a term here in front of our derivative that is not of only x. It includes the dependent variable y. And then we wouldn't have to go over the rest of here. Once we figure out that it's non-linear, it can never become linear after that. So from there, we have the next equation. We have the fourth derivative of y plus y prime is equal to 0. Now we'll notice that this only includes ordinary differentials. So this is an ordinary differential. It is of the fourth order because that is our highest derivative. And, oh, my bad. I forgot to go over whether this is homogeneous or non-homogeneous on the previous one. So let's go back to it real quick. As my bad, I don't want to get carried away too far without telling you. So is this homogeneous or non-homogeneous? Now we'll notice that we do have an additive term here that does not include the dependent variable y. And since we do have an additive term here that does not include the dependent variable y, this is a non-homogeneous differential equation. Non-homogeneous. Remember, if we have an additive term that's separated by a plus, a minus, or an equals that does not include the variable y, then this is a non-homogeneous equation. Now, if we go back to our next one that I so eagerly went to without realizing I hadn't done the other one, we have a fourth order ordinary differential equation. But is this linear or non-linear? Well, we'll notice that the terms in front of here, if you imagine there's a 1 here, right, and there's a 1 here, we'll notice that our terms in front of our derivatives only contain the variable x, or don't contain the variable x at all, but they do not include the variable y, which is important. Since they do not include our dependent variable y, this is indeed a linear differential equation. Now let's go over the homogeneity. Is it homogeneous or non-homogeneous? Now we have no extra additive terms here. We only have 0, and they don't we have no additive terms whatsoever. So this must be a homogeneous equation. We go over the next one. We have our we have e to the sign of x times y triple prime plus sine of cosine of x, and times y double prime is equal to 5. Now, what type is this? Well, this is an ordinary again. So many ordinaries. We have an ordinary differential equations because we don't include any partials in here. Now, what order is this? Well, if we take a look at the order, we'll notice that the highest order right here, the highest derivative, is the third derivative. So this is a third order differential equation. So that third order differential equation. Now, what about its linearity? Well, if we go over its linearity, we'll notice that we have a term here that only contains the variable x. We have a term here that only contains the variable x in front of our dependent terms. And then at the end, we have our g of x. And so this does fit our definition of linearity. So this would be a linear differential equation. I hope you didn't hear any cars in the background. I live in a very noisy neighborhood. Sometimes I wonder if I live by the Daytona 500. Other than that, let's go over the homogeneity. So do we have any additive terms here that do not include a dependent variable? Well, we do right here, this 5, right? This 5 is an additive term, right? It's separated by an equal sign, and it does not include the dependent variable y. So this must be a homogeneous differential equation. If we go over our next example down here, we have 1 over y squared times y prime plus 25y to the 7th, or the 25 times the 7th derivative of y with respect to x is equal to 0. So if I look at this, what is our order, or what is our type? Well, we have an ordinary differential equation. Ordinary differential equation. I know so many ordinaries, but we do have some others in store. Our order type, or not our order type, our order is going to be the highest derivative. Well, we have a 7th derivative right here, and you'll notice that this isn't the 7th power, but because there's a parentheses here, this is a different type of notation, but this represents the 7th order, or the 7th order derivative. It's a bit confusing, but I wanted to include this notation because it does show up from time to time. Whether you're reading textbooks, they tend to use this notation sometimes, and it's all personal preference in the end. I personally don't use this notation. I stick to the prime notation, but if I don't want you to feel confused if you ever do see that type of notation. So next we'll go over the, this is the 7th order. Next we'll go over the linearity. Now, is this linear? Well, if we look at the terms in front of our dependent variables, we'll notice that the first term, the y prime here includes a term that is not of only x. It includes a y. And since this term right here, this 1 over y squared is not of only x, but instead includes our dependent variable y, this is a non-linear differential equation. Next, we'll go over the homogeneity. And if we look at the homogeneity, we have no extra additive terms that do not include our dependent variable. So this must be a homogeneous equation. Next one here, we have something a bit different. We'll notice that we have the third partial of y with respect to x to the second power plus the partial of y with respect to x and z is equal to e to the 3x times sine of x. We'll notice that this, if we look at our type here, this is an ordinary differential equation that's actually quite inordinary. We call it a partial differential equation. This is a partial differential equation. Now, if we look at the order is going to be our highest derivative. So we have our third partial derivative right here. Third partial, this seems to be the highest one. So this is indeed a third order differential equation. Now, if we go over our linearity, in front of our terms, do we only contain x's? Well, we'll notice in front of our derivative here, we only have an x, and in front of our derivative here, we only have a term of x, which is a 1. Remember, there's ones in front of here. We only contain terms of x. But what you'll notice is that if you go back to our definition, it says y and its derivatives are all of the first power. So if we check ours, we'll notice that this isn't of the first power right here. This is instead of the second power. And since it's of the second power, it does not meet our conditions for being linear. Now we'll go over the homogeneity of this. Now you'll notice that we do have another additive term here. We have an additive term that does not include our dependent variable. And since it does not include our dependent variable, then this must be a non-homogeneous equation. And our last example here, we have the term the partial of y with respect to x, x squared and z, plus 5 times the partial of y with respect to z and x, and the partial of y with respect to x, and plus sine of x e to the x squared is equal to 0. This saying all these equations out does take a toll on my throat. Sometimes they can be quite confusing on how to say them. Hopefully I said that right, and if I didn't, I'm very sorry. Sometimes I do forget how to say stuff notationally. So on our first, we'll notice that if we go over our type here, well, these are partial differentials, so this must be a partial differential equation. If we go over our order, well, our highest order here is the third order here. You'll notice that it's with respect to x and then z. So that means we took the derivative of y with respect to x, and then with respect to z, or with respect to x, and then with respect to x again, and then with respect to z. So that's 3 derivatives we took. So this must be a third order differential equation. I wanted to include this notation as well because it does pop up from time to time. It isn't the most common notation, but it does pop up from time to time, and I'd rather you not be blindsided seeing this and being like, oh, what is this, and how can I read this, and how can I do this? Well, this is exactly the same as the notation above right here. These are just different ways of expressing a partial differential equation. Next, we'll go over the linearity. Well, is this linear? Well, in front of this, we only have a function of x, and here we only have a term of x, and in front of here we only have a term of x, and that is our only dependent variable. So this must be linear. Because we only have, in front of our dependent variables, we only have terms of x. We go over our homogeneity. We do have an additive term that does not include our dependent variable y, that is this term right here. And since we have an additive term that does not include our dependent variable y, then we have a non-homogeneous equation, a non-homogeneous equation. Now, I'm sure there are some different situations that I haven't gone over here, because we have, four different classifications, and each of which could be any combination of different types and orders, and linear, nonlinear, and homo, non-homo. So I hope with the definitions I gave you and the examples we've shown today, that you could figure out the type and the order and the linearity and the homogeneity of any differential equation that comes your way.